first of all, there's something called waves be in phase and waves be out of phase. So you have to know what is called be in phase. For instance, let's say you have this. So let me increase the. Now you have a wave of this form. With the another wave. This is a wave A and wave B. Can you see my screen? And can you also hear me?
Sir. Yes, sir.
Okay, fine. You have this. Now, this is, for instance, a wave here getting to, this is trough, and also getting to crest and crest at the same time. So this type of wave, they are said to be in phase. They are said to be in phase or in step. Another language is also called, they are said to be in step, where they have, this is trough, and crest. So for instance, you have in this way. So let's say this is the amplitude of this wave. Amplitude of this wave is, okay, let me change it to color. Amplitude of this wave is this amplitude A. This another amplitude A. It doesn't matter. They can be identical, they might not be identical. Identical means they have the same amplitude, the same wavelength. So they might not be identical. But for instance, let's say they have the same amplitude. So in this case, if you combine these two waves together, that's called being superimposed. You are going to produce the resulting amplitude will increase. So you are going to get something bigger than this. So it's going to be of this form. So meaning the amplitude of this one is now 2A. See, you are adding together. So the same thing for also 2, you have 2A here. So that what it means, that the resulting amplitude increases. But when it comes to resulting amplitude can be either zero completely. For instance, when the waves are out of step. So let me give an instance. You have this, and you also have this type. Fine. You can see now, if you look at this very well, you see, okay, let me divide it into two. Let's say this amplitude A, this also amplitude A. For instance, you have trough and you also have crest. This is on negative, normally on normal x-axis graph. This is on negative. This is positive. If you also look at it here, this is negative, while this is also positive. So if you are finding the resultant wave of this one means that A plus minus A. That gives what? What is it going to give? A minus minus. Open the bracket. What will it give us? Vanessa, can you hear me?
Sir.
Can you hear me?
Yes, sir.
Hello?
Hello.
Yeah, can you hear me?
Yes, I can hear you, sir.
Hello?
I can hear
Okay.
you.
Okay, open for this particular one. This is on negative axis here. So A plus minus A. Open this bracket. What's it going to give me? Do this
0.
mathematics. What's it going to give me? This one.
0.
0. So that means the resulting amplitude is 0. So that one by the state level, fine. So in that case, going to be this is 0. So that will be the amplitude for this. For this one, you are adding together because both positive. So this one is out of phase, while this one in what? In phase. So that's what it means. So let me go back to this. Okay, yeah. So that's what I have here. So when I say either increases or it decreases. So it decreases, so it increases when they are in phase. So that's what I explained here. So the next one is decreases when they are out of phase. Is that understood?
Yes. Yes, sir.
Okay, fine. Okay, good. So now we have the next. This is according to the syllabus. So because I've already planned, I have not planned according to the syllabus. So whatever you see here is the way the syllabus asks us to do it. So the next thing in the syllabus is principle of superposition of waves. This principle is also the same thing by asking you to define interference. Take note. The question say define or explain interference. So it is same thing by stating the principle of superposition of wave. So this answer is for the two, is for the either you have to state the principle of superposition of waves, or you have to define interference. You will get there now, but just take note. So the answer is for the two. The question can say define interference or state the principle. So it's the same answer.
Yes, sir.
Now it states that when two waves meet, the key word here is you have to talk of the key words here. You have to meet or are superimposed, or two waves overlap. That's the key. It's a two-mark question. The question principle is 2 marks. So I'm also into, I think I have, so it's a 2-mark. I'm an examiner. 2-mark question. So the key word is two waves, the wave missed. Then the next thing one, the resultant displacement equals sum of the individual displacement. That's the key word there. The resultant displacement equals to sum of the individual displacement. That's the second mark. So when two waves overlap or meet or are superimposed, the resultant displacement equals to sum of the individual displacement. This is what I did there. So this, for this one, resultant, this is the resultant for this one. Sum of this, what of this one is also for this one. So that's the principle of superposition of waves. So the next thing, when waves are superimposed, there are two phenomena that can occur. There are two phenomena that can occur. Number one, that is called formation of stationary wave. That's number one. Formation of stationary wave. That's number one. So these stationary waves as a result of superposition of waves. Am I communicating? Are we
Yes, sir.
together?
Yes, sir.
Okay, fine. No, that's called stationary wave. Stationary wave now, one of the stationary waves are formed when two waves having same. I will send you this I will send you this note after you send me your email. I can forward it to you from anywhere you want it. I want it from beginning or from superposition. I can cut it off and send it to you. So that will be better. There's no need for you to write. Is that okay?
Yes, sir.
I will forward it to you. So I will cut it to whatever you want it. Now, stationary waves are formed when two waves having same frequency, amplitude, same frequency, same amplitude, and traveling in the same speed. Please, these are the key words. Has to be there. Same frequency, same amplitude, traveling with the same speed in opposite direction, overlap or meet. When you have two waves, they have the same speed, same frequency, same amplitude, and they are traveling. And the overlap, how does it form? So let me write in a plain. Okay, let me start. So how does it form? For instance, this is where you generate the waves. There must be source of the wave. Let's say you have the source here. Then there must be something called either screen or a reflector. A reflector to this. There should be a reflector here. Okay, we have a reflector, or you call it screen. Now, if a wave is traveling like this, a wave travel like this, fine. It's meant when it gets to the reflectors of it comes back like this to the source. So when the two of them now overlap, that is called stationary wave. Number one, the key word, they must be opposite. Or to start with, they must be of the same type, meaning that they have same frequency, same speed, and same amplitude. They must be opposite and they must overlap. These are the key words you are looking for. They must be opposite, they must overlap or meet, or they are superimposed. Now, turn into this. So it's going to now be in this form. So it will be in this form. It will be a sine waveform. So you have a wave traveling. Fine. So let me put this 1 minute is traveling like this. So let me put the arrow on it. Now, when you get to the reflecting surface here, it reflects back. So the one coming back, let me put in another format, another one. So let's say this is the one coming back now. So the one coming back with superimpose. So this is the one coming back. So that's called secondary waves are formed. You can see the one traveling and that one coming back. They are both superimposed. So overlap. That is called stationary wave. Now, when you now form this, there are 2 points that can be identified. That's what you have here. The 2 points can be identified of stationary waves. Number one, node. Node, point of zero displacement. You can see now, this is where zero displacement, zero, no vibration. So at this particular point, wave does not vibrate. So vibration is at the least. So that means the air molecule fibrate list at this particular point, these are called nodes, zero displacement. So all these place, this maximum point here, we call the antinode. So we call the antinode, A for antinode. So that's what it means, A for antinode. So this is what we have, maximum vibration, maximum displacement. That's called antinode. So that's what I mean by 2 points could be identified. One, node, point of zero displacement. Second, or antinode, point of maximum displacement. Now, we can now express this. Take note of this. Note that all points within adjacent nodes or antinode vibrate in phase with the phase difference of, I think I will get to this point later. What I mean by phase difference, I will get to it later. So I will explain in London that phase difference. Within adjacent, they vibrate in phase. Now, we want to express the distance between node or antinode or antinode to antinode in terms of wavelength. So this is what I have here, but let me do it here. Now that I have, if you look at it, this is our node, N is here, N is here. Now, if you look at it now, normally under waves, this is a complete 360. This is 360 degree. Yeah. So that means this place is what 180. Are we together? So this is also what 180.
Yes.
Are we together?
Yes, sir.
Okay, fine. Now, if you look, thank you. So if you now see from node to antinode, this here is a quarter of 180. That's 90 degrees in terms of 90 degrees. That means you are dividing 360 by 4. Now, from node to antinode, it is 1/4 of a wavelength. Because this is a wavelength, this is a complete wavelength, a cycle. From here to this place is a wavelength. So that means from here to here is a half a wavelength. From here is a quarter. So when you have, you can also now have node to node. That is lambda over 2. That is dividing by 2 from here to here. That is 180 divided by 2. Now you can have as many. Let me now combine. You have A, N, A. Now let's see what's it going to give us. From A to A, you can see now A to A. You can see now A to A is going to be lambda over 4 over 2 because A to A, it has to be N first. It has to be A to N, which is lambda over 4. N to A, that's lambda over 4. So lambda over 4 plus lambda over 4, that will give me lambda over 2. So A to A is lambda over 2 plus. Now from A to N is over 4 quarter, lambda over 4. Then N to A, another lambda over 4, lambda over 4. So if you do everything together, I think it's supposed to give you lambda. If you do the mathematics. So that's what I have here. You're combining together as many as possible. So you can see here. Do you have any question to this point?
Yes, sir. May you please explain? I didn't understand that part.
Okay, this part. Okay, again. So let me start again.
That from
Let me
node
start again.
with the 1/4.
Okay, from node. Okay, let me start from over 4. Okay. Now, let me try to wipe this. Now, this is what I mean. You have a complete to and fro cycle like this. So when you have this, you have 180. Now this is a wavelength under a graph. Okay, complete for instance. You also have things like this. Let me start again. Things like this. This is a wavelength. So this is a wavelength. This one is a wavelength. And the distance from here to here is lambda. The same thing from here to here is lambda. The same thing from here to here is also lambda. That's called a wavelength. From here to here, that's a wavelength. The distance between this to this, okay, that's a wavelength. Okay, that one's noted. Now,
Yes,
if
sir.
it's a wavelength, that means from here, okay, thank you. From here to this point, here to this, and to this point, that is a what? Half a wavelength. That is half. Is that one understood? Over 2?
Yes, sir. Yes, sir.
Okay, fine. Now, if I'm looking for this place, okay, thank you. If I'm looking for this place now, that means I'm
What?
dividing half by 2. That's me. That's 1/what? 4.
Yes.
Okay, fine. So let me also do it this way now. 1/4. So let me put it this way. So here now from, okay, let me label it like this. Let me just label it as A, B, C, D, E. Now, that means A to B, it is lambda over 4. We are dividing by 4. B to C, it is lambda over 4. Then C to D, it is lambda over 4. Then D to E is lambda over 4. So add up these together, or this. Yeah, do the mathematics, the 4 of them. Let me see what's going to give you at your hand.
Say to give you lambda.
Thank you, lambda. That's what you have from. That means from, everything is from. So making it clear like this. So let me write it down. So that means A, from A to this, A to E straight, A to E is lambda. So the journey of A to E can take place, that is A to E, A to E can take place as A to B plus B to C plus C to D, then plus DE. So that's give lambda. Is that understood?
Yes, sir.
So now coming back to this place now coming back to what I have here. So if this analogy is clear, if all this is clear now, so let me now come back to what I have here. Was you able to write it out? Or some question were able to, you knew the idea. Now, so if you now look at it now from A to N to A, that is N to A. What's it going to, in terms of lambda? That's lambda over what? Over 4. That's a quarter. Are we
Yes.
together?
Yes, sir.
Okay, fine. Thank you. So you can also have, let's now say this A to A. A to A means you can't get A to A, you have to come back to it. You have to move from A to N, N to A. A to A means A to N plus N to A. So that's what it
Yes.
means. So A to A, thank you. So A to N is lambda over 4 plus another lambda over 4. That's lambda over 2. Is it clear?
Yes.
Okay, so
Yes.
that's what you have here. So, okay, you understand now. So that's how you have all these things. So you can see now A to, you can do it now, N to A plus N to A is lambda over 4, A to N, lambda over 4, N to N, lambda over 2. Add up together, that will give all this. Is that taking?
Yes, sir.
Okay, fine. Okay, that's that. Now, the next of topics is experimental determination of scenario wave. There are, the syllabus says, you should explain how to determine scenario wave. And it depends on the method you ask to explain. I think like about 3 or 4 methods according to the syllabus here. It depends on what you ask to use. So using what is called a stretch string, you have a string pegged at one side, at one end rather. So you have a string. So using this, you have a string. So you have a string here. Let's say you have a string. This is a string in this form. So you peg it at one end here. So it's either you move it either up, or you're moving up and down, or you're moving it in and out like this, in and out to compress and extend. So you are generating waves. So that's called the spring. So how does it work? The scenario wave can be set on the stretch string by connecting one end to the vibrating to an immovable point called node where it does not move, and the other end to a moving blade called antinode. So as you connect in this way, as you are moving it in and out in this way. You are moving it in and out like the moving and out. It will compress it, it extends. So you are going to generate waves at a particular point. So when the frequency of the moving blade equal to the frequency of the string, then stationary waves are formed. The vibrating, which is called the antilobe, has its own frequency of vibration. You moving the wave, the string in and out, has its own frequency. By the time the two frequencies are equal in magnitude, then stationary waves are formed. So that means moving, of course, going to moving in and out, because this one moving, if you move it in like this now, so that means you compress. So you compress. So if you also move it out like this, so you extend. So they are not what opposite. You can see now, let's say A and B, they're not opposite. And you should know that before we can form stationary wave, the two waves must be what? They must have the same frequency, like I said
Yes.
earlier, and they must overlap. So you can see now they must have the same frequency and overlap. Look at this statement here. When the frequencies of the moving blade, the frequency equals to the one of the frequencies of the five of the string, stationary waves are formed. So that's that on that. Two, using the air column. So it depends on the question. If the question asks you to experimental, so the question has to be specific. This is what they want you to use to explain. Explain in terms of string, explain in terms of air column. So air column, we use a closed pipe. A closed pipe is a pipe that is closed at one end. So you blow air. That is what is called a signal generator. This one generates waves, signal generator. You connect a loudspeaker to it. So wave passes through there. So as the air travels through this air column, so I don't want to affect that. So you have the air column here. So as the air travels like the when this one travels through this air column, fine. It travel when it gets here, it reflects. It will reflect opposite again. I know what that one means. When you travel in opposite, they overlap. What happens? Stationary waves is what is formed. So that's all. So as you travel, that's what is happening here. So you can now see the incident progressive sound waves from the loudspeaker are reflected back from the closed end of the tube. Yeah, when it gets here, they reflected back. So that means the incident, the reflected one will now meet the incident. Come again here. Let me come again. So this one you incident, this is incident I. So this one is reflected back here. So the incident is still coming out this way. This one is reflecting this way. Of course, along the way, what happens to both of them? They will meet. Because this one, they will meet. So when the two of them meet or overlap or are superimposed, so what's the next thing? Stationary waves are formed. Are we together? Hello, are you there?
Yes, sir.
Okay, fine. So the two, the wave reflected meet the incidents with the form scenario wave. So at what? At length. You will understand this one later in the length n/4, length over this. That's a close to. See, that's going to be later in the course of the lesson. See there. So three. So there are three ways, three methods that can occur. Three, using microwaves. So first one, you have to understand each of them using the string, two, air column, three, a microwave. So that's how to determine that. So a microwave, you have a microwave generator. So it's just like it has, so let's say this is a word now. You have this place as your microwave, you incident this way. So it together as a core reflector, it get reflected here. It will get reflected here. So everything is following the same process. Only one, two things changes. Still follow the same process. So a wave traveling from microwave. So direct a wave at a metal plate, and the microwave reflect back to the source. Yeah, you can see now. This is the source. This is the metal target. Metal target. Oh, sorry. Metal target. Now it get reflected back. Fine. So get reflected to the source. There's something called a probe receiver. That one detects. What do we use it for? We used to detect the high intensity, either high intensity. We need to detect intensity, either high or low. We also used to detect whether maximum or minimum, either maximum or minimum fringes, either bright. Okay, let me see. Let me list something here. So a probe receiver here can determine the either high or low intensity. That's what it does. 2, it's also determine what is called maximum, either maximum or minimum bright fringes. Bright fringes. Yeah, comment across this later. Or dark fringes. Dark fringes. So can determine it. You can also say high amplitude or low amplitude. It can also determine those ones. You can also say maximum or minimum. So anything that represents something high, maximum or minimum. So that's what it does. Now we have, now move a probe receiver around in the space beyond the transmitter and the reflector. So this is transmitter, the source. This one means a reflector, that's a deflector, a detector, either transmitter or a detector, can also be a detector. So a probe meter, let's say this is a probe meter here, fine. So you move it, you are moving it in and out here, front and back here, yeah, or left and right. Along the way, what happens? It will detect. So move a probe receiver in the space between the transmitter and the reflector until the position of high and low intensity are formed. So what does the high intensity represent? What does low intensity represent? Observe. Stationary waves are formed between the transmitter and the reflector. So the position of the high and low intensity corresponds to nodes and correspond to antinode and node respectively. You know, antinode means maximum displacement. That is high intensity. Antinode node means zero displacement. That is called low intensity. Low
Yes.
intensity. So, okay. You want to say something?
No, no, sir.
Okay. Okay, fine. So that's how. Now, still everything is still under diffraction. Anything to the end of this lesson now is under superposition of waves. So everything. So we are going to look at everything under superposition of waves. So diffraction now. Diffraction also occurs when a wave passes through a gap or through a slit and the wave spreads into geometric shadow. So the key words here, or the key words are, number one, a wave passes through a slit or a gap. That's one mark. Then the wave spread. That's two marks. So this one into geometric, that's if I'm to mark now, that's what I'm looking for. I'm looking for wave spread. Then I'm looking for waves pass through a slit. So that's diffraction. So it's a 2-mark question. Try to define diffraction, explain diffraction, 2 mark. So diffraction occurs when in fact you can also cite, you can also write in a short way that is diffraction just a color wave passes through a slit and wave spread. You have gotten your full marks, the 2 marks. So that's all. So that's 2 marks. So that's the key words here. Passes through a slit or a gap, or and also a wave spread. That's all. Now, the degree of diffraction now expressed by a wave depends on this certain things. It depends on the gap or the gap. It depends on the size of the gap or size of the slit. Also depends on the wavelength, the strength of the wavelength. There is more diffraction where the size of the gap is compared with the size of the wavelength. So what meaning? Let me explain that. Let me explain it here. Now, you have this opening. This is an opening. And you have this particular line here. You have this particular line. These are called waves. You have this line. Fine. Now, the distance between these, the distance is called wavelength. This distance here is lambda. This distance you can see between these waves, that's called wavelength. So it's represented by lambda, the distance. Now, look at the size of the lambda. If you look at this now, look at the size of this lambda from here to and look at its size. It's almost the same thing. So in this case, the wave is going to bend more. Diffraction will occur more. like this, and it will bend more. So in this case, but if you look at another scenario, when you have the bigger, you have the wave like this. Okay, you have this wave. The distance between this wavelength, distance between them wavelength, and you now have this gap. You see now, look at the size of the wavelength. Then look at the size of the gap. Look at the size of the gap. So this person will just pass through without deviating. This will just pass through undeviated, just like this one. This person is a very tiny, slim. Okay, this is slim human being, and this is the door now. And let me look at it now. Let me use this analogy A and B here because the door. This is the door, and you have somebody. So this is the size of the person. Look at the width of the person. So you should know that this person can be able to pass through this door without any problem. So in this case, it only bend little. Totally bearing little. But in this case now, especially if you have the size, almost the same size, or let me even do this in such a way that let me try to do something with this so that to really make sense enough. So let's say it's like this now. Fine. Look at the opening. Look at this size. And look at the size of thing to pass through. This opening cannot contain this person. So this person has to bend. You have to squeeze yourself before you can pass through. That is called diffraction. So bending around. So spreading around a gap. This is called spreading. The wave passes through, when it passes through like this, then passes through a slit, then the second spread around, spread. So that's second mark. That's called diffraction. So it depends on this. So that's what we have here and everything. Okay, that's what we have here. Fine. So this is second phenomenon that occurs from superposition of waves. This is called interference. And I said the other thing, interference, define interference is the same thing by saying states the principle of superposition of wave. So it's the same thing. So interference occurs when two or more waves meet, overlap, and the resultant displacement equal to sum of the individual displacement. So that's all. Now, constructive interference. We have two types of interference. We have constructive, and this is where you have to understand this concept. Many questions on that ways they used to come from. Many questions come all aspects, but majorly these aspects because this aspect is also linked with another aspect, constructive interference. Let me find out. Are we together? Hello, are you there?
Yes, sir.
Okay, fine. So constructive interference. The construct now, when can we say constructive interference occur? When can we say it occurs? When can we say it occurs? The condition for interference to be constructive. Number one, the question has to state. The question is just states. So minimum of 2 marks here. Number one, the wave must be in phase. Two, the path difference. There's something called path difference. Path difference must be n lambda. You will not stop there. When you say the path difference, you state the path difference as n lambda, and you must write this where n start from 0, 1, 2, 3. We need to be careful here. Let me come back here. So the path difference, that's it. My path difference, I used to use this delta S as path difference. So it's n lambda, that's for construct interference. So you are not going to say where n is equal to 0, 1, 2, 3, and so on. You have to put it and so on. You have to put this dot and so on. Now, what it means? It means for first constructive interference, that is first one occurs at n is equal to 0. Second occurs at n is equal to 1. So third occur at n is equal to 2. But yeah, I think you get the logic now. That's what it means. So for first construct interference, it means n is equal to 0. So what happened? First, that means the path that is path different. Now, first occur, that is path different, the first one occur. So that means what should be the path difference for first one? What would it be? Path difference for first one. Yeah, making use of this one. Let me see. Yeah, n is equal, it occurs at n is equal to 0. But from here, so what will be the path difference for first one? Yeah, what will be the change in x path difference? What will it be in terms of wavelength? Let me see whether you get it. Logic. Yeah, yeah. What will it be here? Remember, n is equal to 0. Put n to be 0 here. So what are you going to get? When you multiply by lambda, what are you going to get?
0.
Is 0. So for the second one called n is equal to n. Oh, yeah, put it here. What are you going to get?
Lambda.
Lambda. Thank you. So for the third one, what are you going to get?
Lambda.
Hmm?
3
Oh,
lambda.
this is correct. Sorry. This should be 2. This is 2. It's 0, 1, 2. Sorry. What are you going to get?
2 lambda.
2 lambda. That's all. So all these are called path difference. So in another way, you have to know something here. I put it to you as it occurs. Path difference, that the path difference must be n lambda, where n is 0, 1, 2, 3, and so on. The first one is starting from 0. N0 means the first one. It can also be put this way. That is so. The path difference for construct interference, the path difference can either be 0 or whole number of a wavelength. You can see now. You have 0 or whole number. What's the whole number? If we do the next one now, you are going to have 3. If you do the next one, that will be 4. So when the path difference is either 0 or whole number, what whole number? You are getting 1, 2, 3, whole number of wavelength. Get 1 lambda here, 2 lambda, 3 lambda, 4 lambda, 5 lambda. That's for whole number of wavelength. So when you have path difference to be 0 or whole number of wavelength, that is called constructive interference. Am I making sense?
Yes, sir.
Okay, so you should be noting all this point. So when the path difference is either lambda n, where n is 0, 1, 2, 3, and so on, or you say path difference is 0, or 1 lambda, 2 lambda, 3 lambda, 4 lambda, and so on. It's either 0 or whole number. That is called constructive interference. Another thing now, phase difference. Don't mix the two together. Path difference is different from phase difference. Phase difference, we call it phase angle. What's the path difference? What's the phase angle? So what's the from? It is we will okay. I think after I will have dealt with this earlier before interference, before superposition of waves. Path difference. It should be earlier notes, earlier. But let me quickly just bring it in. So path difference for construct interference, it is 2 pi n, where n is this and that from 0 as well. So what formula for calculating path difference? Is there in my early, but because we did not start from beginning, path difference 5, phase difference rather 5, represented by 5, is giving us there are two formula. So we can use okay, T over capital T times 360 decrease, or you can use this 2 pi delta x over lambda. Yeah, that's the path difference. This one is in terms of degree or degree. This one is in radian. So you can say in degree or radian. Yeah. This one in radian. In radian. 2 pi over lambda. Yeah, 2 pi delta x over lambda. Yeah, that's all. I think so. Yeah, yes. Let me see. Now, what do we, this one is, for this particular one, it's called time difference. This little time, this t is the difference in the time, different in times of the two waves. So time difference between the two waves, between the two, two waves. So between the two waves, where there is the period of any of the wave. There are two waves now, period of either of the wave. either the first one or second one, either of the wave, either of the waves. Now, this one in distance is called path difference. So delta S here, this delta S is called path difference. Path difference, or distance between the two waves, or distal apart between the two waves, and path difference, or distance apart between the two waves. Now, how do I get this formula? That's what I want to know now. Like I say, path difference in this. For okay, fine. So can I scroll down?
Yes.
Okay. Now, I said I'm making use of this now, which is a 2 pi delta x over lambda. For construct interference, for constructive, delta x is n lambda. That's what we started from. You can see now this is called difference, n lambda. This is this. If I should put it here now, that means my phi, that will give me 2 pi. We have n lambda over lambda. So what happens? This will take up this. So I'm going to have 2 pi n. So that my phase angle now, that's 2 pi n. That's what I have in my notes. So that's why I got it here. So that's why I set it out here. So that's all. So far different. So in this case, I have this. I want you to generate 4 second thought for me. So for phi, if you have this, I have phi as 2 pi n. I have this. So remember, n start from 0, 1, 2, 3, 4, and so on. So first one is n is 0. So what happens to phi at n go to 0? What are you going to get? Put n to be 0.
0.
Is that? This is
0.
2. This is 2. This is okay, 0. Fine. Come on. For put second one, n is equal to 1. What are you going to have there?
2 pi.
2 pi. So 2 pi. So what is that next one?
6 pi.
No, this next one now. This next one.
4 pi.
4 pi. And that's how it works. So that's how you can get. So these are called phase angle or phase difference. So when you have 0, you have 2 pi. Pi is 360. You see, 1 is 180. 180 degrees. So you have all these, we call it constructive interference. So these are the things that must be in place before we can form constructive interference. Now moving on to destructive interference, it refers to, for interference to be destructive, it's going to be wave must be out of phase. Path difference now. Path difference must be n lambda plus lambda over 2. N also start from 0, 1, 2, 3, and so on. N must be this. So if I'm going to work with this, for destructive interference, path difference, it is n lambda plus lambda over 2. Lambda over 2. So plus lambda over 2. Now, so we have this. Remember, n is starting from 0, 1, 2, 3, 4, 5, and so on. Now I want us to look at it in another way. Well, yeah, put the first n to be 0. I want to get path difference. For the first one, when it's got to 0,
0.
yeah, what I get?
0.
No, the old is not 0. The old is, are you so? No,
Who
look
what?
at it very.
The whole
They are
formula.
together. It's a formula. Put into the formula. This is a formula for that. Yeah?
Oh, it's lambda over 2.
Thank you. Lambda over 2. Come on. Next one. N is got to 1.
3 over 2 lambda. No,
Okay.
is it? That's what
Ah,
lambda has half. Yes.
3
3 over
lambda over
over
2.
2.
Next
Yes.
one.
The next one is 2 plus half, 2.5. 5/2.
lambda, and so on. So you have 7, you have 9, you have 11, and so on. So now, did we get 0 here at all?
No.
Thank you. So let me compare to the first one. So this is called, let me compare. I want to make some comparison here in order to summarize. For this is called destructive. This is destructive. Let me use this destructive interference. For constructive, we obtain 0, lambda, 2 lambda, 3 lambda. So this is destructive. This is constructive. So I want to make things clear. I want to put together. You can see now, this is called constructive interference. So what's different? For constructive, we are going to have 0 and whole number. For destructive, part different must not be 0. Neither must it be whole number. Because is it whole number? No. This is going to 1 lambda over 2 is not whole number. Everything is not whole number. See now, for this one, they must not be 0 or no whole number. That is destructive. When it is 0 or whole number, that is what constructive. Does it make sense?
Yes, sir.
Okay, fine. So moving ahead. So now the same thing, phase different. How do I get the same thing? How do I get the phase different? Yeah, let's work it out. This is the formula for phase different of that one. For that, how do we get the phase different? Remember, the phase different I call theta L is 2 pi. Oh, sorry, yeah. This is a phase different. I have 2 pi theta x over lambda. For this particular one, we have 2 pi lambda bracket. This is called n lambda plus lambda over 2. Now what we have for constructive. Remember, this is what we have here. This is it. Okay. So putting this one here, what can I do? I can factor lambda out here. Yeah, I can factor it out. That's lambda. This is lambda already. Factor it out. What are going to have? N here. That's lambda over 2. Am I right?
Yes.
That's 1 over 2 rather. So this will take up this. I'm going to have 2 pi, then bracket n, then 1 over 2. So open the bracket, I have 2 pi n, 2 pi n plus 2 pi times 1 over 2. So definitely it's going to give me 2 pi n plus pi. That's what I have there. So 2 pi n plus pi. That's how I got it here. So you can see now that's all. 2 pi n plus pi, where n start from 0 and so on. So that's a different, that is constructive interference and destructive interference. Now, I have some points to be noted here, a lot of them. Yeah, that's how I used to form my notes. So you have to know this point. So if two source interference ranges are to be observed, so what will happen? Number one, you have to sit down and read these notes.
Yes.
They must meet or overlap. They must meet overlap. That's it. 2, they must be of the same pi. 3, they must have the same direction of polarization. So if the question is 2 mark, you have to give any 2. If it's 3 mark, you give the 3 marks. 3 marks. So that's all. A point for 1 mark. So they must meet. They must have the same. They must be of the same type. They must have the same direction of polarization. Number 2 on that note, there's something called coherent waves and coherent source. What's called coherent? Coherent waves, wave with constant phase difference. That's all. It's a 1 mark question. It's a 1 mark. Why I'm telling you, because I'm used to all this. I've been on this Cambridge level since 2020. 2015. I started into taking Cambridge A level 2015. So that was 9 years now. Yeah, I remember it was even April 2015. So 9 years plus. So I know if I see a question, if I tell you I know those questions, the mark that they use to attach to the question. So I'm used to it. So coherent, the question says define what are coherent with, or what is coherent. Just a wave with constant phase difference. That's all. It's a 1 mark. So if the next question now say, why do we know that waves, or what happens? Constant phase, wave with constant phase difference. For waves to have constant phase difference, what will happen? They must have the same frequency. So when you have waves that have the same frequency, automatically they are going to have constant phase difference. The phase, let me even put it, phase difference is going to be the same thing. That's called constant phase difference. So same frequency. Same frequency me come here, let me explain this. Now I've listed something today under phase difference, which is T, small t over capital T, then multiplied by 360 degrees. How does it work? Let me try to do something here. You have this okay, let me try to do something here. You have a graph, this fine, you have this graph. Let's say this is a graph, a label as A. You have another graph labeled as B, starting from here and be passing through this, through this, through this. So label this way. So it will be this way. Fine. This is another way. This one label this as wave B. What's the difference in time between them? You can look at what means different by time, different in time. This is what I mean by small letter T is the different in time. So different in time means different between this and this, from here to here. You can see now. See them. Or
Yes.
from here to here. So the time different, or from just different between, you can see now, from here to here. So that time difference, this is again to be against time. So time difference between this and that's called small letter T. This capital T can be period of, it can be period for A or period for B. Anyone, the same, they have the same period. Now, that's all. If we now set it, let me assume I want to calculate the phase difference. Let me assume now I want to calculate phase difference between the, it's supposed to, even from here, it's supposed to be something that will give me something like, it should be like around 90, because this is 90. So I want to get that one now. Over for, let me say it, let's stay. Okay, let me say period T here is 4 seconds. And the timing between them, time between them is 1. Let's say small letter T is 1 seconds. That 1 seconds. Of course, it's going to be 1 second. Because if from here to here is 4, from here to here is 4. So that will give me 3, that will give me 2, that will give me 1, that will give me 0. If I'm to label this one now, yeah. So if I'm to label this, if I'm to label this, no, let me use something different. If I'm to label this now, so it's going to be on 0, this is going to be on 1, on 2, on 3, on 4. You can see now. This is going to be 5, this will be 6, this is going to be 7, this is going to be 8. So if you consider A, if you consider A, that means from here to that's a 4. That's a period. If you consider B, from here to here, that will be 5 minus 1. That's also 4. So small letter T now is 1. So let me try to calculate 5. So that will give me 1 over 4 times 360. That will give me 90 degrees, which is reasonable, which is correct, because from here, this is a quarter. You can see now it's on a quarter. 90 degrees. So phase difference now is 90 degrees here. But what means constant phase difference? Meaning that constant means the same. And for we to achieve constant phase difference, frequency must be constant. And don't forget that under wave, we have frequency as 1 over period. Can you hear me?
Yes.
Now, so if frequency, let's say frequency for A, frequency for B, we have 2 waves now. So that also give me 1 over period for A and period for B. So if I do it from here, what happens? 1 over period, 1 over 4. Period is 4. This is also 1 over 4. That is 0.25 hertz. You can see now, that's the main constant. That's what I mean by constant. That means constant phase difference. That means they're going to have same frequency, because what frequency is constant. Then the period is going to be constant. Does that one make sense?
Yes.
Okay, so that's called, that one I mean by the statement that they have coherency. So what you just need, define coherent waves. Wave constant phase difference. So when can we say wave have constant phase difference? That means they must have same frequency. Coherent sources, it's the same thing, just to refer to source that produce what? The source that produce wave constant phase difference. So to come to another 2 sources now, interference. I think there were 4 methods here. So you have to define interference, experimental verification of interference. It depends on what you have to do. It depends on which methods you have to use. Using water waves. The first one, using water wave, we have sound wave, we have microwaves. We also have light waves that we are going to use. So it depends on what you are asked to do, which one you asked to use. Now, on this, using water waves, this involves use of water waves passing through 2 gaps. So this one is just like Young modular 2 gaps, forming by 2 gaps. So what I mean by 2 gaps, you have, it's going to be this one like this. That's one. That's called slits, double slits. So you have the wave, the source of the wave here. So the wave traveling this way. So the whole, let's say this is the wave traveling, fine. So when they get here, they will spread out like this. This one will spread out like this. The second also will spread out. The one passing also will spread out. You can see now. See that they overlap. So where they meet like this here, that is called constructive interference. Where they overlap, constructive interference. If you have to draw a line that represents constructive interference here, I didn't draw it properly, but let me just say. So this is what they asked to do. Construct interference, of course. But for destructive, where they did not meet at all, you can just draw anyhow. You can draw it here. Fine. They do not overlap. The two of them do not meet. But where the two of them, you have line like this, you have line like this, and you have another line like this superimposed. So where they overlap like this, that's called constructive interference. Where they pass through without overlapping, meeting, that's called destructive interference. Is it clear?
Yes, sir.
Okay, fine. So through a gas barrier, the two water are diffracted at the gap and then interfere in the space beyond. So that's what I mean. So that will interfere in the space beyond. They are diffracted here. That's diffraction occur. So this is space beyond. Space beyond, they what? They overlap. That's the method there. So that's the first one. Second one. For second one, you have using a sound wave. For sound wave, we have a sketch here. What is you it, no before the after this, just send you can tell Mr. Ajiro to give you my email. Just send me email, or Mr. Ajiro will send your email to me. So I'll be able to cut this and send it to you so that for you to go over to read. So after the class. Is that clear?
Yes.
Okay. Now using the sound wave, this involves the use of loudspeaker that are connected to the same signal. Why is it same signal generator? Why? Why? Because as soon as a question like that, why not use different signal? Why? So that so that the waves can be coherent. Remember, a singular generator provides a single frequency, same frequency throughout. And under coherence, we know that the waves coherent means constant phase difference. And we can only achieve that when the two waves have same frequency. Therefore, it is very, very imperative for us to use a single signal generator so as to produce a single wave. And that will be in line with being coherent. So the purpose of a single one is to what? So that the waves can be coherent because of single frequency. Does that one make sense?
Yes, sir.
Okay, fine. So that's our filming frequency. Now, you now have it this way, signal generator. You have two loudspeaker. So two source, one travel this way, the other one travel the other one. So they overlap, the same thing. So where you see they meet together, it's called constructive interference. Where they do not pass through, they do not meet, that's called destructive interference. The two speakers are separated from each other. Two, sound wave generated from the signal generator are passed into the two speaker. So this one will generate sound. So the sound passes here, also passes here. After that, this one comes out. This also comes out. So what happens? So that one comes
Um.
out. Okay, so the overlap. So look at it now. The waves diffract from the speakers into the space beyond and they interfere. You can see now. So diffract. I've said about diffraction. Let me go up. Okay, here. There was diffraction here. So diffraction means they will bend. You can see now. So that's why I say they are bending. The wave diffracts and move onward. The wave diffracts. So what they different towards space beyond where they will overlap. Overlap means they form interference. Note, the two speaker must be connected to this. Oh, it's even here. The two speaker must be connected to the same what? Connect to the so that the sound wave will have same frequency and be coherent. Oh, I didn't even know I noted it in my notes. So be coherent. Two, after the diffraction from the two speaker, destructive interference occurs where quiet sound is heard and constructive interference occurs where what a loud, how do I know it's loud? This is where they meet here, the overlap. That's called constructive. But any other points, that's called destructive. So that's what I'm saying. So that was it. So this third method, using the light waves. Using light waves, this involves directing light wave from a laser. We use what we call laser through the slits. They are still using the slits. They are using opening, two slits, where the wave diffracts through the slits. Then when the wave diffracts through the slits and then fall on a screen, a series of equally spaced dots as seen on the screen. These dots are referred to as interference fringes. So let me read it before I explain. Bright interference fringes are formed when the waves are in phase. When we also have what's called dark interference. Fringes are formed when the waves are out of phase. So let me quickly demonstrate it here. That one light passing through the slit. This is more or less what we call a young double slit experiment. We will get there. So a young double slit experiment. This is what we have at slit. So we have a screen here. Fine. So under the screen, you wave traveling like this. One also coming like this. They will meet here. If you draw another 2, 1, 2, another one coming like this, also meet here. That's called a series of equally spaced dots here. So let me now spell this thing out here. Let me try to spell it out. So I have, okay. Now, I have the dots. You are going to find this is a dot. Let me first of all spell it this way. Equally space and equally space. Now, you have another dot in between. These are called dots. We have bright. Let me now say this is the one I use as let me use this one. Let me call this one bright dot. This one will be dark dot. You have bright, you have dark. That's how it operates. Bright, you have dark, then you have bright. So that's all. So when you see bright dots, bright fringes, dark will follow. If you see dark, so that's how it operates. We see bright, bright, dark. These are called fringes. Bright occurs for where the waves are arriving in phase. That is called constructive interference. Dark fringes occurs what is called destructive interference. So that's what's going to happen there. So we are still going to look at this later under your double experiment. How do we do the calculation? So the fourth one, which is the last one under the experiment here, is using microwave. Microwave transmitter is directed at two sources as well, two gaps like that. In a metal barrier, the microwaves are diffracted at the two gaps. The first thing occurs, diffraction must occur. It's going to be something like this. It's going to bend like this. Another one will bend like this. So that's what we are just saying. Both of them are saying the same thing, but just in a different ways. Space beyond, where they can be detected by using a probe receiver. The probe receiver is moved around so that ranges of high and low, we talked about this earlier on, can be detected. High correspond to bright fringes, low correspond to what? Dark fringes. So that's just simple as that. Now, next, young double slit experiment. You need to understand the concept very, very well because most questions are with they are under this aspect. Young double slits experiment. I don't need more story here. So you can have all these slits. There's something called slit width. Slit width means the opening here. Slit width and slit separation. You understand the two together. They are two different things. You have this. Hello, are you there?
Yes.
Okay, fine. Now, slit width. This is called slit width. This place, slit width. That's called slit width. Slit width. Now, this one is called this particular one. This from here to here is called slit separation. You separate them. That's called slit separation. So you understand it. Don't mix them together. So the slit width, the width, and the separation. So that's all in that. You form screen here. This is where you are going to form your bright fringes, bright and dark. This time between this is called delta D. Okay, I think I have everything labeled D. So what is A? What is X? Okay, put it there. This is a formula that connects them. Majorly, we use this a lot. We use this. By the time we start solving question now, based on this now, you understand what I'm saying. So we use this a lot. So A is called slit separation. X, you have wavelength, distance between the slits and the screen. Then distance. Now, this X, be careful with it, understanding distance between two bright fringes or two dark fringes. That's all. That is called fringe separation. Let me come back here. Distance between dark and bright, dark and dark or bright, bright. So let me now explain it better here. How many? 1, 2, 1, okay, 1, 2, 3, 4, 1, 2, 3. Okay. The distance I mean here now. So the bright to bright, that means from here to here. That is our X, bright to bright. Another from this to this. That's another bright to bright, another X. From here to here. Okay, no. Let me make it separable. Clearing. Okay. From this bright to bright, this is X. So that what that X represents. The second. So from bright to another bright, that's another X. So that's all. So that's bright to bright or dark to dark. So you can work in terms of bright to bright or dark to dark. Here now, I can say now, why am I using bright to? Because bright is starting from bright to the beginning from bright, end from bright. So I'm going to consider the highest one here. So I'm not going to use that to dark here. Because that is in between. Now that is X. Then I assume that we are giving distance from here. This distance. I want to look for it. This distance, let's say this distance is given. This distance, the whole distance from bright to bright. So starting from bright and the bottom bright and top bright. Let's say we are giving 20 meter. So what should be my value of X now? Okay, that's how to calculate X. If you are not giving me X directly, bright to bright, 1X, bright to bright, another X, bright to bright, another X. Are you listening to me?
Yes, sir.
So
Divide by
meaning that, thank you, plus this is equal to what? 20. That's 3X is equal to 20. We can get our X. That is that. That's see what they draw for us like this time. Now, let me now assume that it wasn't drawn like this. It was drawn for us like this.
I have a
You understand what I mean by? You said?
yes. I have a question.
Okay, okay. Okay, okay, yes.
It's always only from bright to bright or dark to dark.
No, no, no. It doesn't. That's what I want to go now. It can be from dark to dark. It depends on what if it's drawn for us or the question says so. So let me say we have this this one now. See what I have here. So let me claim this out. Let's say we drop ahead. Look at question drop from here to here. They label this to this for us as 20. I want to clear X. So that means we are using what? We are making what? Dark and dark here. So that means I'm going to make use of dark. You can see now this is bottom dark and top dark. This is what they call 20 meter. Are we together?
Yes. So it's divided by 2.
Oh, divided by 2. Thank you. Thank you. I appreciate that. Thank you very much. That will be this. This is X. This is S. So I think you have gotten logic now. Is it clear?
Yes.
Okay, fine. So that's all it depends. So take note of that because that's what is giving student problem. So that one that X represents. So note this. Note all. In fact, all these points are very, very important to note. This one answers some many theory questions. Many theory questions that are not calculation. Number one, we have X varies as lambda. This means that the higher the wavelength, the more the distance between bright to bright or dark to dark. That's all. Or another language, separation between fringes increases. That's another language. Because when you say distance between bright to bright increases, that means fringe separation increases. That's another language. So when you have higher wavelengths, you are going to have higher X. What mean of X? Distance between bright to bright or dark to dark increases. So when you vary that wavelength, this means that fringe separation increases when frequency decreases, vice versa. Yeah. So fringe separation increases when frequency decreases. You can also have another one here. This means that slit separation increases, fringe separation decreases. So here is the slit separation. So you should know this from that formula. Now, number 4. For number 4, the waves that are coming from the source, they might have the same amplitude or the same intensity. Amplitude and intensity, they are related. That was the earlier one. It's not in part of where you want us to start. It's the earlier one. But let me quickly give it out. Intensity varies as square of amplitude. That's 1. Meaning that you can have A1, I1, A1 square. You also have I2, A2 square. So note this there at your hand. Note it down. That's 1 point. That's factor of any intensity. This intensity varies as 1 over this as well, distance from the source, meaning that you can have I1, R1 square is equal to I2, R2 square. So R is the distance from the source, I is the intensity, A is the amplitude. You can have this. You can also have the last line that intensity varies as well, frequency, square of frequency. So you can have your I1, F1 square, I2, F2 square. You can have this to take note. Factor affect intensity. So I used to summarize the theory by saying intensity varies as well, A square varies as well, S square varies as 1 over R square. So that's all. That's the summary of that. And don't forget that intensity means power over, okay, let me write it down. Is in the earlier, is better to give you the whole note self. Yeah, you like it. By the time the others one is very understand comprehensive. So I made it comprehensive. My students used to appreciate this note. They used to print. They also asked them to print in the don't write. They appreciated all this note. So intensity itself is giving us power over area. And the area we consider power. Area is the word by R square. That's all. This is the formula that combine intensity. So note it at your hand, note it down.
Yes, sir.
Okay. Now, what even led me to this myself? Okay, okay, I know what led me to this. So we have the source here, we have this, double slit here, the wave coming here and coming here, they superimpose on the screen here, fine. The two of them may be of the same intensity or of different intensity. That is, let's say this is the wave A and wave B, They can be of the same intensity, with the same amplitude, or different intensity. So let me go back to my point of saying, if the intensity of the light from the source increases, intensity that to do with brightness. So take know all this point over. That we see when you understand what I'm talking about. All this, you appreciate all this point. If the intensity of the light increases, so what happens? Bright fringes become brighter because intensity that to do with light. Bright fringes become brighter. No effects on dark fringe, and no effect on fringe separation. Whatever, look up, whatever happens to intensity, whatever makes the intensity to be increased, then that thing will have effect on bright fringes.
Yes.
Whatever makes intensity to be decreased, that means it will have effect on dark fringes. So get it right. So if intensity increases, the effect is going to be seen on bright fringes. No effect on fringe separation, no effect on dark fringes. Now, the same thing, if the intensity of the light decreases, it will have effect on the bright dark fringes. So no effect on the bright and so take note of these 5 and 4 and 6 now. Intensity of the fringe become darker. No effect on bright fringes and no effect on fringe separation. Is it clear?
Yes.
Okay. Now, for destructive interference to occur, the amplitude of the two waves from the sun must be equal. Yeah, come here. We want to form destructive interference. Okay, let me first of all note something here. Destructive interference is equivalent to bright fringes. Maybe it's writing in words there. Bright fringes, or you call high intensity, so it's the same thing. All this one, or let me put this way: destructive interference, high intensity slash high amplitude mass. All of these correspond to bright fringes. Bright fringe. They correspond to bright fringes. Now, sorry, dark fringes. Sorry. Oh, I made this up. Sorry, there's a mistake here. There's a mix up here. Dark fringes. That's low intensity, low amplitude. Sorry for that. I didn't know I was talking about this. That's low intensity, low amplitude. All these, any language correspond to dark fringes. Dark fringes. So the opposite, constructive interference, high amplitude, high intensity correspond to what? Bright fringes. So see it that way. So just see it that way, bright fringes. Now, for me, if I want to have destructive interference to occur, many dark fringes. This is now dark. Let's say I have dark fringes here. Dark fringe. Look at the point here. It said for this now, for destroying that, the amplitude of the must be equal. So amplitude of the two waves arriving there must be equal. So amplitude of this wave A and A2, or instead of this A now, because A is for amplitude. Let me use this one, wave 1 and wave 2. So amplitude for wave A must equal to amplitude for wave 2. So the two of them, when they are equal, we are going to form dark fringe. Destructive interference occurs. So take note of that. But this constructive interference to occur, amplitude must not be equal. So either one must be greater, meaning that for constructive interference, amplitude of 1 for wave 1 is not equal to amplitude of phase 2. Are you with me?
Yes, sir.
Okay. So it's not equal. So what are you now saying? So it's not equal. So look at the points. You are not look at the point 8 now. Now, point 8 is saying if the amplitude of the wave coming from the source are not equal. So what happens? If they are not equal, that means we are not equal. If they are not equal, look at when they are not equal. The amplitude are not equal. What do we have there?
No destructive interference.
Okay. For constructive interference, the amplitude of the waves must not be equal. Now, if they are equal, they are not equal. If they are not equal, that means we are moving towards constructive interference. So I become brighter. You can see now. See what I do. No complete destructive interference. Because destructive interference, of course, it's a 3-mark or 2-mark question. Question asking. They will not say that equal. They just said the amplitude of the two. Now, maybe the question C. Now, the amplitude of the two are no longer equal. So state and explain the effects on the fringes. That's what that question used to be. So the amplitude of the waves are no longer equal. State and explain the effects on the fringe form. When you should 2 marks. When you state it, 1 mark. You explain, 1 mark. So you should first now go back. Amplitude are not equal. What am I forming? I'm forming what? Constructive interference. So that means there is no complete destructive interference. Dark fringes become what? Brighter, because I'm moving from destructive to constructive. I am moving from dark fringes to bright fringes, and no effect on fringe separation. It does not affect fringe separation. So take note of this. So if the amplitude is no longer equal, or the question will say the amplitude of one of the waves now half is reduced. That means they are not equal. The question says the amplitude of one of the waves is reduced. That means they are no longer equal. So what happens? No complete destructive interference. Dark fringes have become brighter, and no effect on fringe separation. So take note of that. Oh, I don't know when this. No, it's going to be another day, but let me just let's say pick this, if I can pick a bit. So this is another one called diffraction grating. Similar to that, you have to understand the effect of them. So diffraction grating interference is maximum, always maximum. We use maximum. There's no minimum. Maximum is occur. Maximum interference occur. The path difference is given like this. So this is, we have this and theta is equal to n lambda. N also start from 1. What we know the slit spacing. Let me say I put it like this. Okay, slit spacing. Towards any number of other wavelength, angle between the zero order and the maximum order. Zero maximum is zero order maximum and the order being considered. This one is in 2 ways. You can see now, just like mirror. You have first order, this is also fourth order. The horizontal one is called zeroth order. So first order, for first order, this is theta. I call it that. I have used this one for first order. For second order, so the name of this order, the highest order bears the name, the highest order. So in this case now, what order is it? This one, we call this second order. We call it second order interference. Second order maximum, rather. Let me explain what I'm saying here. I may also start again from that, but let me next time. It's on Wednesday. So let me say I have this and I have this. This is this. I have this 1, 1, 2, 3. So the name of this now, this is, if I had to name, what's the name of this order? It is called third order, because the highest one is third. We have, this is 1, 1, 2, 2, 3, 3. This is 0. So the name is what? Third order maximum. So the highest will be at the name. Assume I have another one here. That 4, 4. So that becomes what? Fourth order maximum. First order maximum. So that was going to be the name here. That will be the name here. So in this case, so first order